Hi everyone, this is Analog Circuit Design, Lecture 14, Frequency Response. I would like to acknowledge my advisor, Michael Flynn, for his lecture notes, and then also Dr. Sung-Jung Lee for his feedback. Here's the outline. First, review some basics, and then we will do some frequency response calculation. First, review of dBs, decibels. So decibel is a unitless ratio of power, and is represented as 10 log, so this is log 10, and then P1 over P2. This can be confused easily because some people just put 10 or some people put 20, but it really depends on what the input would be. So if input is power, then we put 10 log 10. So we multiply 10 if the input is power. But if the gain is voltages, then we put 20. So this is important. So you need to be clear, like when should we multiply 10 or when should we multiply 20. So is this consistent? Because yes, because power is V square R, right? So it's like 10 log V square R, let's say VO, V square R. R is the like a load resistor, load impedance or resistance. So this would be, so basically this is 10 log P gain is 10 log this, and then we assume that there's a resistors are same. So this definition is, let's assuming that RF circuit. So in RF, we assume that the input resistance is at 50 and then output resistance is also 50, something like that. So we assume input R and output R are the same. So it turns out we can just remove this R, and now it becomes 10 log VO VI square, which is 20 log voltage gain. Then there is an important number to memorize. For example, if power gain is 1, then it's 0 dB. And if power gain is 2, then it's 3 dB. But if voltage gain is 2, so and then this is 6 dB. So this 2 is, be cautious about this 2. When voltage gain is 2, then it's 6 dB. But when power gain is 2, then it's 3 dB. Since we're using log in decibel, so it is also good to review log. So we just add dB decibel values of cascaded amplifiers. So for example, assuming that there is amplifier and its gain is 10 dB, and there's the other amplifier following, and then there's 15 dB. The overall will be 25 dB, right? So we are just add these two, because in log multiplication in linear, because if you do this, this would be like V1, and this is AV1, AV2, then this would be, let's just say A1, A2. This would be A1, V1, and A2, A1, V1. So we're multiplying the gain, and then since we represent these gain as log, we can just add these two gains. If you want to divide it, then we can subtract it. Using log scale is very useful in analog circuit. So first, log scale is more convenient for plotting signals with large dynamic range. So what is large dynamic range? It means like the value has a large range. Let's say we can have like 10 nanovolt, or let's say we have 1 volt. The difference between this is like how many times? 10,000, it's like this, right? So this is what we call large dynamic range. Maybe this example is too extreme, but there is a like common amplifier. I mean, just usual amplifier can have 80 dB. I mean, this is like high gain amplifier, but we can have 80 dB gain amplifier. It means that 10K 10K it means 10K voltage gain. So this 10K is kind of large number. So rather than that, we're using 80 is better. And also, it's easier to visualize sum to plots than it is to multiply. So this is, we already talked about this before, right? If there is gain in decimal, it will be like AV1 plus AV2, right? In dB, because in log scale. So if we have like the frequency plot like this, so, and then usually this will be log 2. We also represent our frequency in log domain. If you have this frequency response of this amplifier, and then if you have this frequency response to this amplifier, and the overall response will be just adding it. So it's simpler rather than just multiply. Here's two components that's dependent on frequency. First one is capacitor, and second one is inductor. In our lecture, we mostly focus on capacitor. So the impedance here is S1 over SC, and then S we will put J omega, which is imaginary number, and the inductance impedance would be SL. So what it says is when frequency is large, what happened to the impedance? It goes to 0, right? So it means that when high frequency, this capacitor looks like a short circuit. In inductor, when frequency is increasing, because frequency is W, right? Well, this is like F and 2 pi F, and then this F is frequency. So if you increase frequency over the inductor, its impedance is getting larger, which means at a very high frequency, inductance operates like an open circuit. But in low frequency, inductor is just looking like a short circuit, while the capacitor is, well, just capacitor. So there's the maybe the side story would be, you know, when you just bond, so you know the bond pad. So assuming that in tape out, let's say this is your chip, and then maybe this is a packaging, and you have to wire bond this pad to the output. So I mean there is like a flip bond, which is more like advanced version, but this is also kind of used like mostly in research. So in this chip, what it says is from silicon to the output of the pad, we have to connect those two pads by using wire. And this wire has a length, right? And any wire has inductance. So usually this inductance is really small. So the inductance, it's like parasitic inductance. So L is small. But it can be a problem if our signal is really high frequency. As I said, the impedance will go up as the frequency goes up. So in high frequency, this bonding inductance may be not negligible. So again, the inductance can be crucial if our target signal frequency is high. Let's see the frequency response of simple RC circuit. So we try to find this V out over V in, and we can just use resistive divider. So because this C is its impedance is actually S1 over SC, and then S is J omega. J is represent imaginary number, and omega is 2 pi frequency F. So V out over V in is 1 over SC R plus 1 over SC, and this will be 1 plus SRC. So our pole frequency is minus 1 over RC. We can also represent, so this is a function of S, we can also represent this as a function of omega, and this will be 1 over J omega RC. Now we got an equation here, and let's draw its frequency response. So we try to draw the absolute value of gain, and that will be is 1 plus omega square R square C square root. And then there's an important frequency, which is pole frequency. That's like 1 over RC. And if this W is the pole frequency, then it will be like 0.7 707. So it's just 1 over root 2. And this is what we call this as a 3 dB bandwidth. So this is actually 3 dB bandwidth. So let's draw it. We can just say, because if we increase R here, it's like in this, and then we can also note important frequency, which is pole, and this will be 0.701 or 1 over root 2. But if you use a like log scale, then it will be like, so at DC, the gain is here, and then the gain is keep decreasing like this, and then here is, well, WP, and then this one that is 20 dB, minus 20 dB per decade. And so it basically looks like this. It's like here, this is Bode plot. And what would be the gain at here? at 0 frequency. If you put 0, and that will be 0 dB, right? Because the gain is 1. I'm saying is, if you put W as 0, which is DC, then this go out, and the gain will be just 1. And this also we can think it like, because if the frequency is really low, the capacitor looks like open circuit. So if there's no capacitor, V in is just equal to V out. So what is pole? Pole is a value of S that causes AVS to go to infinity. So in this case, for our RC example, pole is minus 1 over RC. So the value of S is negative and the real number, and the magnitude is the pole frequency. So let's say like 1 over RC. In Razabi, they say pole, they represent pole as positive, but there's like two different notations. Some people use this notation, or some people use like minus 1 over RC notation. Well, it doesn't matter. It's okay to use both. But in our slide, we're going to use this one. But here, it doesn't, the pole is not actually making this AV infinity, because, you know, so it will be, eventually it will look like this, J omega RC. And omega is real number. So omega is real. So we cannot make our denominator 0. We can plot our pole for RC circuit. So our RC circuit, AVW was like 1 plus J omega RC. And our pole, we can say minus 1 over RC. So in this case, our pole is here. And then, you know, we represent pole as this cross symbol. And here's WP, and then this is 1 over RC. And this is left half plan. Let's look at the gain, what happened at pole frequency. So if you just substitute the absolute value on here, this would be, our pole was minus 1 RC, and this will be 1 plus J, right? And then the magnitude of our gain is 1 plus 1 root. So it's 1 over root 2. So gain drops by 1 over root 2. This is so voltage gain. It corresponds to minus 3 dB gain. I mean gain magnitude, which is power gain, right? Let's revisit frequency response again. So our gain looks like this, and then if we represented it with our log, there is a important frequency, which is pole frequency, and our gain will keep decreasing, right? And it's just like this, and then at this frequency, we're seeing the gain degradation, I mean power gain degradation by 3 dB, and here is 0 dB, so it's minus 3 dB. And we can also just simply draw it in bullet plot. We already did it, but let's do it again. So at pole frequency, we just assume that our gain is same as 0 dB, and after one pole, our gain will decrease, and its slope is minus 20 dB over decimal. I mean decade. And here's pole frequency. In this slide, I brought some paragraph from Razavi book. This is from Razavi book. It's about polarity of pole frequency. This is kind of confusing, but let's just see what it says. So we should point out that the sign of omega in and omega out in the above equation is positive. And these are poles. So their notation is like this. So the pole should be minus omega in, right? And I mean, this is S. In this notation, their omega in is positive. It's positive. But in our lecture slide previously, what we said was, for example, for RC circuit, the pole, W pole was minus 1 over RC, right? So it means that we're using different notation. And then this is also mentioned in Razavi book. Alternatively, here, we could express the values of W in and W out with a negative sign. So this is what our slide note is doing. So we're using a different notation than Razavi. But at the end of the day, it doesn't matter because when we plot graph, we are just using an absolute of pole and zero frequency. So in our lecture slide, just assume that pole is negative, and that this is also has a good advantage because it gives us the information that the pole is in left half plane. Well, so I mean it's good for if you have negative sign in our pole, and just automatically inherit this LHP feature. Let's also calculate the frequency response of common source amplifier. Here we have a load capacitance, but at this moment ignore all capacitance except CL. What it means is that there is like a CGS parasitic capacitance, or I mean that's CGD or CGS or even CDS. But at this moment we're not going to consider it. So just this. And let's draw a small signal model. So it will look like V in and GMV in and RL, RO, and CL. And here's V out. But assume that let's just try to ignore channel length modulation because this RO is a lot larger than RL. We can just remove it. So this is our small signal model. So with this small signal model, we're just going to calculate our transfer function by using KCL. So what KCL means is at a single node, the summation of all the current flow is 0, right? So it says the current flow here and here and here, the sum of those three currents must be 0. That's KCL, which is GM V in plus V out RL plus V out and 1 over SCL, because the impedance of CL is 1 over SCL. And if we just, and this is 0, and then this would be, if we do some math, like minus GM 1 over RL plus SCL. So we will just make it a little like a neat. So separate the low frequency part. So it's like this. And it turns out just this. So you know, the gain of this CS amplifier is this one, right? So it's like assuming that we don't have CL. Assuming we don't have CL, which means CL is 0. Then our gain would be minus GM RL. We already learned about this, right? But since we have CL, we add this part, which means we have one pole. The overall gain with common source simplified frequency response, and we only consider about CL. There's no parasitic capacitance at this moment, and that will look like this. And again, this part, this part is low frequency gain, and this part is frequency dependent part. So why this is low frequency gain? That's because in a low frequency, the capacitor looks like open, right? At low frequency, capacitor is open. So it just removed, the capacitor just removed, then our just normal minus GM RL. And here's the rule of thumb. Pole, which is already here, the pole. What is the pole? Pole is minus RL CL1, 1 over RLCL. In Razabi notation, it's plus RLCL, but it's okay. Just use either. So it says that we see the node at this node. What is the impedance at this node? We see RL, because we ignore RO, RL and CL, right? I mean, even if you have RO, it's fine. We can just use, if you have RL, then it will be just like RL. RO, it will be just like RL. This one. So it doesn't matter even if you include RO. But still, what it says is the rule of thumb that is here, we see the R and C, and then we multiply that, and that will be our pole. So each node has a pole. But this is technically not true. Sometimes if some two nodes are connected, then we may have less pole. But this is just like a usual, like a good starting point to assume things. So each node has a pole. I mean, not always again, but it's a good intuition. So I'm just gonna say but not always. Now let's draw a frequency response. Well, we already draw a gain, right? So at DC, so you should just think about DC. The gain is this value, right? I mean, it should be 20 log 10 this. So we start from the DC, and then the way how we draw is we have a pole frequency, which is WP, and then after that our slope will be minus 20 dB over decade. And so basically at here at WP, so this is 3 dB, right? This is minus 3 dB. Maybe you may wonder why after pole this is minus 20 dB per decade. That's because so our, should I say here, this would be GMRL 1 plus this one, right? If we assume that the WP is larger than, I mean the W, our frequency is larger than, let's say our frequency is larger than WP. Let's forget about the, well, I just put it here, the polarity. In this case, what we said is it will be look like GMRL W, because we can ignore this one. We can just ignore that. Ignore. So our gain looks like this, and then if we put just a 20 log 20 log on omega, this will be just some random, I mean not a random, some a constant there, right? Because in let's just do this. So the first, this part will go to the constant k, and then the rest of them does look like this minus 20 log w, right? Because there's only 1 over w left. So that's why after certain frequency, I mean larger than WP, our gain has a minus 20 dB per decade. Okay, so we're done with our amplitude, I mean the gain. And then what about phase? Next is phase. To begin with, so if we put j omega, then it will be like minus GMRL and 1 over 1 plus j omega RC. And this will be minus GMRL and 1 minus j omega RC and 1 plus omega square R square C square. What we did is we just multiply this part at the denominator and denominator. So the way how we draw the phase is actually arc tangent. Arc tangent is a inverse of tangent. Arc tangent of the ratio between imaginary of AV j omega and real of AV j omega. So this will be minus arc tangent. Let's just ignore this part because they're constant. So because we are looking for ratio, they will not change anything. So it will be arc tangent. What is imaginary? This will be minus omega rc, and then the real will be just 1, right? So it turns out arc tangent minus omega over rp. Well, since we have our omega p is negative, we will just remove the negative sign, and then this is our equation to draw phase. So our starting point is minus 180 degree because our gain is minus. What does it mean? Assuming that we put a sine wave, this is, let's say, V in, then V out would be minus, which means different, the flipped sine wave, which means 180 degree. So let's say our phase is minus 180, and then what happens when W is 0? Omega is 0 at DC. When omega is 0 DC, then this arc tangent, which is our phase, is when 0, then it's 0, right? So it just go here at the DC. And what about omega is infinity? It's arc tangent. So this one, when arc tangent is in infinity, the angle is 90 degree, right? So it's minus 90 degree because we have minus sign at here. So at a very large frequency, the phase goes to minus 90, which is minus 270. And actually what happened at omega p is minus 45 degree. So it looks like this. So this part, this is 45 degree. So this is our phase, and here this part is 90 degree. And let's think about our frequency response in again, low frequency part or in high frequency part. So at low frequency, C is open, so it's just a normal, not a normal, but just low frequency CS amplifier, which is AV is minus GM RL. This is what we've learned in previous lectures. And at high frequency, what happens is so cab is its impedance of cab is getting decreased, which means our gain is decreasing. So at the very high frequency, just assume then the cab will be shorted and our gain will be 0. So it means that it just tells us that our gain is decreasing like this with minus 20 dB decade. Next, let's consider the other all the parasitic capacitance. So there will be CGD and CGS and CDB. And then if you draw a small signal model, it looks like this. So basically it was look like this, right? V1, I mean V in, and then we put CGS here, and then CGD here, and then CDB here. And let's do our same calculation before. We're just using a KCL at the output node. So this will be a little lengthy calculation. So the first one, the current here. So V out minus V in and SCGD. It's because we divided by 1 over SCGD. I mean divided by. So we just multiply SCGD here. Plus GMV in and this current, and then well the current flow these two, which is V out over RO parallel RL, and also the current here, that's also V out S CDB plus CL is 0. So we do some math, like, and then the equation will be this and this, and the result will look like this. Again, similar low frequency gain, because our circuit was basically this without capacitance, because in low frequency we can ignore capacitance. So here's RL, and then here's RO. So gain is GM minus GM, RL, and parallel RO. And then this part is frequency dependent part. So we do a lot of math. If you do a lot of math, and then we can get it from the previous slide. Let's see the pole. So pole is 1 over this, and 0 is, this is positive 0. So the pole is at left half plane, and then 0 is at here. Now let's plot the Bode plot, frequency response. So we have single pole here, right? That will be here, and then we also have 0, which is in right half plane. The single pole at this is left, and WZ was GM over CGD. So basically at 0, the gain will have plus 20 dB per decade. So here was minus 20 dB decade. And now we made 0, so it becomes flat again. It's flat again. Flat. For the phase, so here 90 degree, and then at pole we got 45, and then at 0, here we got here's 45 again, and then at the very high frequency we will just see the minus 360 degree, which is the same phase. Let's divide our region as 3 ABC. First one, A, is low frequency, At low frequency, what we do is we just open every capacitor. So cap is open, and V out, V in would be just GM, RL, RO, which is constant. The next is region B. So what we assume is that V out is basically like gain, DC gain, and then it was like 1 plus OS, actually 1 minus omega Z, 0 omega, well, I'll just say S, and because we have only one pole, it, it it's like this. This is what we have. In region B, what we assume is omega is smaller than omega Z. So if this happens, then we can just ignore this, right? So that's how we got this gain. You see that in numerator we ignore 0 and then just 1. So we have only one single pole, and then it goes as a minus 20 dB per decade. And region C. So region C means high frequency. When we say high frequency, means that W is larger than W 0. So what happens here is that we said, we already talked that if frequency is high, so high frequency, high freq, and impedance of cap, ZC, is 1 over SC, right? And S is J omega, well, J omega. So in high frequency, the impedance of ZC, the capacitor, is getting small. So in our drawing, in our circuit, just here V in, I'm just gonna draw and here is CGD, and here is CDB, and CL. The CGS, we are ignoring it. Why? Because the voltage source is directly connected to gate. So in reality, we do have a source resistor. So we do have a source resistor here. In that case, we have to consider CGS, and that's the real case. CGS plays an important role, but now we decided to ignore the series resistance, so that's why we're ignoring CGS. So here what happened is the impedance through this Z1, it's very small, it becomes very small. Assuming that the frequency is really high, then the signal flows to this cap. So it's like, rather than passing through this MOSFET, it just goes to this way. So it looks like a capacitor divider, like CGD, and CDB, CL. So it becomes like CGD and CDB, CL, and VL. So it looks like this. So what happened is VL over Vin is CGD, just capacitor divider. So this value is here. So the gain is not decreasing. The gain will just be flat when the frequency is larger than 0, WZ. Let's revisit the rule of thumbs. So what we discussed was the pole frequency at node is could be resistant, 1 over resistance and capacitance, which means each node has a pole, unlike we see like here, RC filter, and then here this node pole happens. 0 occurs when parasitic path become dominant. It means that in our common source amplifier example, we had this CGD. So it means that the parasitic path means path to here. So if this like a parasitic path become dominant, then 0 happens. So it's like the gain is directly a function of just capacitor, function of capacitor ratio. You know, if we don't have this, our Boda plot, I mean the transfer function would be like this, right? It just goes to 0, a very, very small gain, right? But because of our this parasitic path, gain is no more decreasing, but just stay constant because of that parasitic path. And then here, this point is 0. And some nodes are coupled together, so these simple rules does not work. It means that this each node has a pole. This is not true sometimes. Next, we will learn about Miller theorem. This is very important part. To begin with Miller theorem, let's look at this circuit. What's the difference? Now we have RS. Before we didn't have RS, but now we have RS. So here we have a question now. The pole at X, as I've said, it will be like RC rule of thumb. R would be RS, right? What about C? So this is a question mark. We do have CGS and we have CGD, but is it just CGD? That's what's related to Miller theorem. And how about here? And P out. So this one, this WP out. The resistance would be, if you don't ignore channel length modulation, this. But what about C? It's also like C would be CDB plus CGD. So this part we'll talk about Miller. So overall this is 2 nodes, 2 poles, and 1 0. Let's talk about Miller theorem. This is very important part. So let's see this circuit. We have some amplifier. Let's just say ideal amplifier, and then we have a ZF here. So our interest is how does this ZF change with this amplifier? let's just calculate things. So assuming that we have Vx here, and then we want to see Z in, right? And then, so it's of course it's not ZF, right? They will look different, and then that's what Miller theorem will try to looking for. And assuming that there is IZ, so Z in is Vx over Iz, right? And what's Iz? Iz is Vx minus X, because the current flow here is the voltage difference divided by ZF, right? So at this here voltage is Vx, and then this node voltage is minus AVX because of this amplifier. And the denominator will be ZF. So if we just substitute it here, it will be Vx. Well, yeah, it's Vx, and then Vx 1 plus A, right? And then ZF. So ZF is basically reduced by gain A, right? So Z in is ZF over 1 plus A. Let's see the example with an actual like component, assuming that there is C. We usually use this Miller effect over capacitor. So here and then CF, and what is C in, right? That's our question. And it becomes C in. C in would be like 1 over SCF 1 plus A. It becomes 1 over S 1 plus A CF. So what happens? This. So CF becomes 1 plus A CF. So it becomes larger by this. So seeing larger cap. And let's see why, like, why does it happen? It's like, so if you change voltage here, what happened the output? So the voltage looks like this. So if this is delta V, then it becomes A delta V. So at this point of capacitor, suddenly its voltage change across this capacitor becomes so large, right? What I'm saying is, if the cap is grounded and there is delta V, then just overall voltage change over capacitor is just delta V. But if you have this at the output, now this capacitor experience a lot larger delta V. Sorry, delta V1 plus A. So since the voltage changes more, the current flows more. When we say current flows more, that means smaller impedance or larger capacitance. So that's how it like intuitively understand. Because of this amplifier, the voltage change across the CF becomes suddenly larger, like 1 plus A times larger, and then effectively we see this impedance as smaller because it draws more current. From what we learned from for Miller theorem, Miller effect, now let's see the input node X. Because we have a source resistance here. At this node, input pole occurs. So here at this node, input pole. So um, according to the rule of thumb, the way how we calculate was it's WP. The pole frequency is minus 1 over RC, right? And R is what? RS. Then what is C? This is our question. And as we said, because of Miller effect, the impedance looks here becomes like smaller, which means the capacitance becomes larger. So again, maybe it's confusing, but the impedance is this, right? So if, well, let me just rewrite it again. So impedance is this. When we say impedance gets smaller, so we need smaller impedance, right? Because of the Miller effect. Cap is increasing. That's the point. Cap increases. So again, smaller impedance means larger cap. So here, smaller impedance means larger cap. Okay, so effective capacitance becomes 1 plus CF. So the pole would be minus 1 RS 1 plus A CF. This is our answer. Because of Miller effect, we see different effective capacitance. This slide shows some like interesting application usage of by using Miller effect. For example, here using a buffer to eliminate unwanted parasitic capacitance. Like our target is we want to remove this cap. So what it says is first intuitively, if you change the voltage here, this buffer just give a same voltage, right? So when we see the capacitor, and in terms of capacitor view, there's no voltage voltage change across capacitor, which means there's no current flows. So this capacitor is just got ignored. This is also, we can represent it with our using equation, because C in was 1 plus AC, right, in this case. Well, CF. If the gain is plus 1, that means gain is minus 1. So this becomes 0. And there's also a negative capacitance. So negative capacitance means now the gain is minus 2 in this case, right? So C in here, C in, and let's say this is CF. C in is 1 plus A CF. But A is minus 2, which means minus CF. This negative capacitance, my friend in Flynn's group, he made an ADC and then he utilized this negative capacitance to cancel out the offset of the amplifier. Well, just long story short, he utilized this negative capacitor to improve the ADC performance. Well, that was presented in 2022 VLSI. So, and what does negative capacitance mean? It means that the current is provided. So what it says is the current is, if we change the voltage, let's say if you change the voltage here, with the normal capacitance, the current flow here, right? But because of this negative capacitance, actually the current is supplied. So that's what negative capacitance. And how does it even work? right? If we apply voltage and then the current flows in opposite direction. So these are possible because we're using this active circuit, active amplifier, which means it consumes energy. So these amplifiers are different from just passive component. Passive component means R or CL. This amplifier is not passive component. That's why we can kind of manipulate like negative capacitance or like even or like ignore, eliminate capacitance because again, because we're using this active energy consuming component. Next, let's use our Miller theorem, apply this Miller theorem to CS amplifier. Let's apply Miller theorem on our CS input impedance. So input is here. So the Zin is a parallel combination of CGS and CGD. We're not considering these parts. And assume that the gain is constant over our frequency interest. So Miller theorem is generally applied only over a range of frequencies. Like for example, at low frequency, low enough that the gain is around this value. And then Miller theorem holds. So what we're going to do is, so this CGD is our interest, and we're going to use Miller theorem on this CGD. Let's calculate the pole at here by using Miller theorem. So like here, this is what we got. Here is X and Vx is, and then V out, and then the gain. So pole at X. So it will be, well, first minus, and 1 over what's R? It's Rs, and then we have to calculate cap. First we see CGS, so CGS, and then we will see CGD, but because of Miller effect, its value is its effective capacitance is larger. So what's AV? AV is minus GM RD, and then for our Miller effect, the baseline was minus A and CGD here. And then this will become CGD effective will be 1 plus A CGD, right? So here A is GM or RD. Just be cautious about this polarity. So this will be 1 plus GMRD CGD. So this is our pole. Here's some assumption. First, A is not frequency dependent. So it makes sense because what we're looking for now is pole 1, so first pole. So our gain looks like this. Our gain is at the first pole, it will go down, but what we are looking at is this area. So gain is before pole. I mean, we're just considering about before pole, so we can still use this GMRD. And the other assumption in here, not an assumption, but the other point is that you see this point. So as I said, to get a pole, we need to see R and then capacitor, which is this one and this one. But you see that, how about these things? Should we consider this or this? So it turns out, no, we can just ignore this because this node corresponds to this node. And then we're assuming that this amplifier controls this node value, this node voltage, this amplifier. So it's like no matter what's like connected here, see L, amplifier is kind of just ignoring it because amplifier has enough power to change this voltage regardless of this. So that's why we're not considering RD and CDB. Let's say they all poles in zero. So there's two poles. Two poles we calculated this in previous slide because this is Miller theorem, Miller effect. Our CGD is amplified, and then we have another pole at the output here, which is RD because there's resistor, and CDB times plus CGD. So this is actually like reverse Miller effect. I mean, in the opposite side, because we can understand it like, as we said, it changes a lot when input change is small here. So when we see it this way, if we apply a voltage change like this, that's what happened, right? Because of this amplifier. The other side of this, oh, actually this is not here. This should be here. So the voltage change here at this node is larger than this node. So this CGD is just roughly, we can just say CGD. So we're not applying Miller effect because, and it's kind of approximation. This is just approximation. And zero, we calculated before. This is same. So zero is GM over CGD. So because we have non-zero RS, so we did in previous slide we did when RS is zero, then we have one pole and one zero, but now we have two poles and one zero, so our frequency response will be like this. So here would be 20 dB, and here would be minus 40 dB, and here would be minus 20 dB again, and here is WZ. Just use an absolute value, and WP2, and here is WP1. So you may wonder, how do we know this, the relationship between them? So usually this pole 1, it has a Miller effect. It's very large. I mean, these value RC is very large, which means lower frequency, and WP2 higher than that because they don't have any Miller effect. And 0, when you compare these two, so just assume that we're not having too small RD, and since we have CDB here more, so this frequency is usually higher, so we put it at the very end. So again, when the transfer function, so this is 20 log gain. AV is voltage gain. When the graph passes pole, then it becomes decreasing, and second pole again 20 dB, so overall 40 dB. To be accurate, it should be decade. And since 0 is increasing 20 dB slope, so it change it to minus 20 dB again. In Razavi book, there is full calculation. They just changes. So these are the whole components the CS amplifier has, and then by using this full small signal model, we can get this one. And you see that the zero is GM over CGD. And with some approximation, we can see that our pole, like approximation with this and this, I mean these two approximation, we get pole is kind of pole is similar to what we predict by using Miller effect. So pole 2 is at this node. So it says that Miller effect gives us a good approximation. Next, we'll look at the frequency response of source follower. Let's calculate the source follower frequency response. To make it simple, what we're going to do is we will neglect body effect, which means GMB is 0, and then channel length modulation, which is RO is infinity, and RS is 0. If you want to see the full response, you can see the Razavi. So first, let's draw a small signal model. It's V in and CGS, CGD, and so CGD is connected to VDD, which is AC ground, and here GM, and here is V1, GM V1, because this is source, and we have CL, and this is V out. Well, V out. Let's use KCL at this node. First, the current here, which is VO over 1 over SCL, and the current flows from here and here. That will be the opposite sign. So minus V in minus VO, V out, and 1 over SCGS, and minus GM V1 is 0. And then we have the other, we need one more equation, which is V in is V1 plus VO, V out, right? Because V in is to use KVL, V in is V1 plus VL. So if we substitute this to here, as a result, what we got is S, because gain is a function of frequency, 1 plus S over CGS GM, and 1 plus S CL plus CGS divided by GM. So this is our result. And let's draw frequency response graph, which is Bode plot. So our pole, what is our pole? Pole is minus GM CL plus CGS, and we do have 0, right? And this would be minus GM over CGS. And what is larger? So Z is later, right? Because in pole they have CL at the denominator, so this is a smaller value. So that's why WP is here, and then 0 is there. So what happened to the gain? It decreases at here minus 20 dB per decade, and then it goes up. Well, not goes up, it's just being flat. So here is flat. And what's this value actually? So let's see the circuit again. Well, what we can do is here to make S infinity, and that will be CGS CL plus CGS. This is because when we see the circuit, if the frequency becomes really large, then it's a CGDS. It's a capacitor divider, so that's why we got this. And how about the phase? Phase is at pole. At pole we got a minus 45 degree. It's like here, and then this is minus 45, and here is 90. And since we have 0, it goes up again. And we have 0 and pole at the left half plane. So LHP. So pole is smaller, right? So pole is here, and 0 is here. You may wonder why don't we see CGD, right? Because there's no CGD. That's because here, because RS is 0. So in our case, we assume that V in and there's no RS, which means the capacitor here, CGD, doesn't matter because we have an ideal voltage source provided at here. So no matter what's connected at this node over ground, it doesn't matter because we have ideal very strong voltage source. But if we have V at RS, then we have to consider CGD too. Next, let's calculate the source follower input impedance. We'll just look at this node. Because RS, we can just add RS. So here, what we can do is we can change it to small signal model. A kind of small signal model. You see that the 1 over GMB is here. That's because in small signal model, GMB is actually GMB VBS, right? And VB is 0. And here, this is drain. And drain is ground. And here is S. So basically, this one just works as resistor. So that's why we can just replace it as a resistor. And in Razabi book section 6.3, with bunch of calculation, we got this number. And then what we do here today is we'll compare this result with Miller theorem, with the result from Miller theorem. Now let's use Miller theorem. So the gain from source follower gain is basically 1, right? So we don't see any CGS because this node and this node is moving as same, so we don't see any current flow here. But more accurately we can use GMB, because in this equation from previous slide, for a full calculation, we also consider GMB. So if you use GMB, the gain would be, this. This one, right? So the C in would be CGS Miller effect. You see note that the polarity is minus because the gain is positive. Why? Because when we do Miller effect, the C effective was 1 plus A C F. So we need this minus sign. So that will be like this. Minus GM over GM plus GMB. So let's just compare this with this. If you assume at like low frequency, then this GMB is larger than CLS, so we can ignore it. And if you do some math, it turns out as SCGS this one. So the CGS is here, and they're kind of actually similar to, so Cin, which is predicted by Miller theorem, has the same value as a full calculation. Well, there's 1 over GMB, but that's not shown in Miller effect. But the point is, we can kind of predict the impedance using Miller theorem with some accuracy. Now let's calculate output impedance. We're going to make some assumption. Well, now we have finite RS, which is series resistance, and also we're going to neglect CGDN, RO, and GMB. I know we have a lot of approximation suddenly, but our purpose to see output impedance is we want to see some special characteristic of this circuit. So it's okay with this approximation. So let's just calculate it. We're using a KCL at V out. That means IT is minus GM V1, right? Because IT is going here, and then we just try to say this and this are IT. So minus GMB minus V1 over SCGS. And what about VT? VT is first minus V1, and then here, and then this one. So we know that current here, so we can just multiply RS with that. That will be minus V1 SCGS times RS. Because we just write it down this here. So if you use these two equations, what we got is the output impedance will be Z out is VTIT. Now if you do some math, it will be SRS CGS plus 1 and GM plus SCGS. And let's see how it looks like. From our previous calculation result, it was 1 plus SRS CGS and GM plus SCGS. So at low frequency, which means S is 0, then it will be 1 over GM, right? Because these two are removed. And in high frequency, let's say infinity, which means S goes to infinity, the gain would be, the Z out would be RS over S over RCGS over CGS, which is RS. So if we set the two value, like here, if RS is larger than 1 over GM, we see this kind of result, which means the impedance is increasing as frequency becomes higher. And this characteristic is special. It turns out when frequency is higher, then if the impedance getting higher or larger, it's an inductor characteristic. So you see inductance, the characteristic looks like this. It's SL and then J omega L. So, and then we can also model our Z out, which is Z out was in the previous slide. Z out was RSCGS times S plus 1 over GM plus CGS S. So we can model like this, and then if we do some analysis, the inductance is the equivalent inductance is like this. You can also refer to our book. So is this inductance good or bad? In this source follower, it can cause ringing. It's like if we apply V in like this, then maybe output can be like this, which is not good, right? But also we can actually utilize this inductor as our equivalent inductor. I mean the inductance. If you refer this article, they show the actual applications for using this as an inductor. The thing is, making inductor consumes a lot of area. It's really like just maybe it looks like this. There are various type of inductance too, like some inductor looks like well, eight figure or some just square. So this can be actually useful circuit. And the next is common gate frequency response. For common gate frequency response, note that node Y has very little effect on node X. So very little impact on node X. Why? Because here the input resistance is really large, so Z out is large. So which means the node out is not impacting X that much. We have two poles because we have two nodes, one node at X and one node at Y, and just make this the CGS and CSB as CS, and the CD is CGD because this gate is ground actually. This is like AC ground, right? So the capacitance between CD and G is just go to ground. So we can just merge these two as CD. So pole at X, this would be W like PX. Let's just say W in. W in is, well, 1 - 1. And what's the cap? The cap is CS, right? CS and R. R would be RS parallel 1 over GM and 1 over GMB, right? Because if you see this way, the impedance at this way, this would be 1 over GM and 1 over GMB. What about pull out at Y? So this is pull out. This would be -1, and we have RD and CD. We're ignoring the impedance seeing it here, this part, because this is a large impedance. So we're not using this. And so overall voltage gain would be like this. This would be our the DC gain. So this is again always this is DC gain. Well, I'm not saying DC gain. DC gain is kind of sounds not good. Low frequency gain. Well, DC gain is also true though. And then we have this W in and W out. Now let's look at the cascode. We already learned about it. So CGD will be, if you go to see here, C effective is 1 plus GMRD CGD. But what about common cascode? Is CGD has an impact of from Miller effect? With some approximation, what we can do is to see the resistance here is GM2. Well, this is M2. GM2, 1 over GM2. This is 1 over GM2 plus GMB2, right? So the gain is, what is it? The gain is minus, just roughly, I mean, at this node. We can say X. The gain V, which is V in over Vx, is minus GM1. And what we do is just multiply the resistor here, right? Here, because you see this part, the gain here is a GM RD, but we see the impedance as this, so we'll just multiply those two, which is GM2 plus GMB2. Okay, so this is, well, let's say just minus 1. So the effective CGD will be like probably roughly double CGD. So it's better in terms of compared to this, right? Because it's increased a lot, but here just double. So as discussed before here, so CGD effective is like double CGD. So if you calculate the pole at input node, like this node pole, this would be minus 1. What is a resistance RS times, we just assume also there is CGS, so CGS plus 2 CGD.